Okay, good morning. In today's lecture, we are going to see single source shortest path problems related with the graph. Okay, so far we were discussing about all the algorithms related with the graph search, minimum spanning tree. Okay, here we are going to see the last category of graph algorithm, that is single source shortest path. This is also from the same textbook prescribed in your syllabus, Corman, Introduction to Algorithms. And here, as an introduction, what are actually single source shortest path problems? Okay, here we will, when a graph is given, maybe a directed graph, then we will choose a vertex as a source. From that source to all other vertices, what are actually the shortest path possible in the graph? Okay, this has got some real life applications. Maybe the graph actually is a weighted graph and the edges will carry some cost of construction or cost of travel or distance, like that. Then we will be very much interested in finding the shortest path. If it is a distance, we are always interested in finding shortest path. And there are two important algorithms for finding single source shortest path. One is Dijkstra's algorithm and another one is Bellman-Ford algorithm. And here we will consider graph, a weighted directed graph, and the graph is described by an ordered pair v comma e. Remember that it is a directed graph and associated, this is a weighted directed graph, and weight is associated with edges, and the weight function you can write, it's a function from e to the real domain. And the path, the shortest path, what is actually a path? There will be a source and there will be a destination. How you are reaching from the source to destination, that listing, your travel listing is nothing but path. If there is no direct one, maybe there is a direct path, or otherwise you are going through some intermediate stops and you are reaching at the destination. This will list the path. But we are interested in shortest path. And for this, each path is associated with a weight. And what is meant by weight of a path? It is simply the sum of the edges present from source to destination. That is actually the weight of the path. And if there are 5 paths from V0 to Vn, then we will compute the weight of each such path, and the minimum weight will be the shortest path. And this is how we are formally define those explanation for a shortest path. Let delta uv be the shortest path weight from u to v. Then if there exists a path from u to v, then we will be computing weight of all such path. Then minimum will be chosen, that is actually delta uv. And if there is no such path, then infinity, very large value. Shortest path from u to v is any path from u to v where weight of that path is the smallest one, that is delta u comma v. And apart from, for the algorithmic purposes, we are using one more variable, pi of v, as with our previous graph search algorithms. And pi of v, pi denotes the predecessor or the parent in the visit, predecessor of v on the path. And this is a graph, a directed graph. Okay, here if you are taking 1 as the source vertex and maybe 1 to 2, okay, just for an example, consider the query is find the shortest path from 1 to 2. Then you can see 1 to 2 there is a direct edge, and the weight of that edge or path is 50. And you can also travel like this, 1 to 3 and 3 to 2, and the weight is 30 plus 5, 35. You can also travel like this, 1 to 4, then 4 to 20. The weight will be 100 plus 20, 120. You can also travel like this, 1 to 5, 5 to 4, then 4 to 2. The weight will be 10 plus 10, 20, 20 plus 20, 40 only. Out of all this weight, the lowest or the least weight path is 1 to 3 and 3 to 5, that is 30 plus 5, 35. That is actually the shortest path from 1 to 2. Like this, we will be computing shortest path from 1 to 5, 1 to 4 and 1 to 3. This is actually the single source shortest path. One vertex will be taken as the source. Then shortest path from that source vertex to all other vertices in the graph is computed. 1 to 5, 1 to 4, 1 to 3 and 1 to 2. And these are the different types of shortest path problems. Single source shortest path. Find shortest path from that source vertex to every other vertex present in the graph. Single destination shortest path means the destination is single, then we will be finding shortest path from all other vertices present in the graph to that destination. Single pair shortest path means we are only interested in finding shortest path from specific vertices, say u and v, u to v. Only one pair is computed. And all pair shortest path means for all the pairs in the graph. This is slightly complicated all pair shortest path problem. And in this lecture we are concentrating on single source shortest path. And before going to the algorithm, there is a concept of negative weight edges and a cycle. And here you can see there are three vertices in the graph, A to B, B to C and C to A. Okay, three edges are there. And the weight are 2, 3 and negative 6. And here you can see if we are traveling back, okay, the edge is 2 plus 3, 5, 5 plus 6, negative 6 means minus 1. At minus 1 cost you can reach here. And the problem with this is actually a negative weight cycle. Going from A to B to C has a cost of 5. A to B, B to C has a cost of 5. But going from C to A has a cost of negative 6. So that the total cost of one cycle from A back to A is negative 1. The total cost of two cycles you can see negative 1 plus 2, 1, 1 plus 3, 4, 4 plus negative 6, it is 2. The total cost of two cycles is 0 minus 2, that is negative 2, which is less than the cost of one cycle. That means we can always find a lower cost path by doing one more cycles. And this should be eliminated. Okay, this cycle should not be present in a graph. This is a constraint. And this negative weight edges should not be there. As long as the graph has no negative weight cycle which are reachable from source node, we are okay. Okay, this is the assumption behind, the important assumption for computing single source shortest path. Okay. If our source vertex is V1 and our destination is Vk and our path is something like this, V1 to Vi, Vi to Vj, then Vj to Vk, that is subpath 1, subpath 2 and subpath 3. Then we can decompose the path from P1 to Pk into several subpaths. One is P1i, I hope you are getting it. Second one is Pij. Third one is Pjk. Then weight of P1k will be weight of P1i plus weight of Pij plus weight of Pjk. Assume that P1k is the shortest path from 1 to k. Then weight of P1k is the lowest cost. And this should also be the shortest path. Okay. And this is an example we are considering for finding the shortest path. And this shortest path actually looks like, okay, the travel of or the path, the shortest path is like a tree. Therefore, there can be many shortest path trees. Okay, here you can see this is actually a shortest path. Okay, shortest path, the tree will be here. And how to compute this, that is actually an important one. And before going to the algorithm for estimating the shortest path, there are two important sub-algorithms. One is the initialization. Initialization means the graph will be given and a source vertex S is given. For each vertex in the graph, the distance, the initial distance is set as infinity and there is no predecessor that in the path because we have not yet visited. Therefore, you can see that the predecessor will be set as nil and the distance of the source vertex, since we are starting our journey from the source vertex, the distance is actually 0. The distance is going to be 0. And here the question, this is an important algorithm we are using in finding the shortest path, relaxing an edge. Okay, what is meant by relaxing an edge means we are improving the shortest path from U to V by finding or discovering another path. Can we improve the shortest path to V found so far by going through U. Okay, that is a question. We already have discovered one shortest path from path to V, but the question is, can we improve it by going through another vertex? Okay, the question, can we improve the shortest path to V found so far by going through U? And if so, we have to update the distance and we have to update the predecessor. Okay, don't worry about these two algorithms. This will be cleared as we go through that. Okay, the relaxing an edge is simply like this: U V W. Okay, if the distance of V is greater than distance of U plus weight of U to V, then D of V. That means we have found a shorter path from V to we have found a shorter path than the previous one to V and update the weight, then that will be updated and the predecessor will be changed. Okay, this we can have a clarification with the example. Okay, then here you can see before relaxation. Okay, this is an example of the relaxation. Before relaxation, where is V? Okay, this one. Distance of V is greater than distance of U. Okay, the direct path 0 to 10 was 10. Okay, then through this path you can see 7 to 7 plus 2 9. 9 is less than 10. Okay, that means the question is asked, though there exists a path from S to V, there is a shortest path from S to V, can we improve the weight of that shortest path? Yes, we can improve it by going through S to U and U to V with a lesser weight than 10. Then we have to update the weight. Distance of V, that is greater than distance of U. Distance of U is 7 plus weight of this edge is 2. 7 plus 2. Then what we have to do? Update distance of V as this particular value 9. Then predecessor of V is not S now. Predecessor of V will be U. Okay, once again go back to the algorithm. If there is a shorter path than the original one, how will you check that formally? Distance associated with V is greater than the new shortest intermediate vertex, distance of U plus weight of that edge. Then update the weight. D of V is equal to D of U plus weight of that. Then predecessor will be changed. Here once again, though we have a direct path from S to V with the weight 10, we will be giving the weight as distance of V as 10 and the predecessor of V as S. Now later we found that one more intermediate path through U, that is S to U and U to V. And what is the cost actually? Is it a better path than the previous one? Then we have to update it. For that we will be asking the query like this, whether the distance of V is greater than distance of U plus this direct path. Distance of U is 7, 7 plus 2 9, distance of V is 10. 10 greater than 9. No, therefore you have to relax. Relax means distance of V is updated with this value 9 and the predecessor, the parent of V is not S. Actually this path is via U. Therefore the predecessor of V will be U. Okay. This is actually the relaxation algorithm. Okay, this is really useful. Here also you can see in the graph we were considering before. Okay, where was that graph? Here you can see that 1 to 2 there is a direct edge 50, but later we realized that 1 to 3 and 3 to 5, that is 30 plus 5, that is a better path compared to this path. Therefore we will be updating this and the predecessor will be 3. Predecessor will be just giving an information how we are traveling through that. Okay. And Dijkstra's algorithm. The problem is solve the single source shortest path problem on a weighted directed graph for the cases in which edge weights are non-negative. Okay, what is the major difference between Bellman-Ford and Dijkstra's algorithm is, in Dijkstra's algorithm the edge weights are always non-negative. The weight cannot be a negative value. And here you can see that the same example is considered. There is no negative weight and the basic approach is maintain a set of a set S of vertices whose final shortest path weight from source to S has been already determined, and repeat. Okay. This is a little bit messy. We will go to the algorithm directly. Dijkstra, the input is the graph, the weight function and the source. The graph, the weight function and the source actually. And here the initialization. What actually the initialization does? Initialization does that. Initialization actually does that all the vertices, the distance from the source is very large value infinity except S and the predecessor as nil. Then this capital S actually denotes the set of vertices, they are already part of the shortest path. Okay, and this Q is actually the minimum priority queue, and in the minimum priority queue all the vertices will be inserted. And remember that the distance of all the vertices are actually infinity, that is the initialization step. Okay, initialize single source shortest path. I request all of you to go back and see what is actually the single initialization. Initialization is nothing but all the vertices in G will be, the distance will be initialized as infinity and their parent is actually nil except for the source vertex. Source vertex distance will be 0 and the parent will be nil. And while this minimum priority queue is not empty, then extract the minimum. Okay, obviously the first vertex extracted from this minimum priority queue will be our source vertex S, and U is our source vertex S. Then S, that this source path will be S union U. Then for each vertex V adjacent to U, all the adjacent vertices of U will be considered. Relax UVW, that means we are just finding if there is a better path from U to V than the previous value U to V, and the weight function will be passed. Okay, this is the algorithm, and for this you need to understand what are the initialization phase does and what are actually the relaxation does. I told you that there is always a path to V. Okay, now the distance will be initially infinity. Then you will be checking whether there is a better path less than infinity from U to V. Okay, if there is one such directed path exists, then you can replace the value, you can relax the edge as we have seen with the example. Okay, we select a single vertex at each step, we relax each edge leaving that vertex. Okay, that is the relaxation is the heart of the Dijkstra's algorithm. And here you can see the initialization. This is an example. S is going to be the source vertex and all other vertices T, X, Z, Y, the initial value is infinity, and here if S, all vertices will be inserted into the Q, and the distance the based on the distance extract minimum will be deleting the lowest distance vertex, and here you can see 0 is the lowest value compared to the infinity, therefore the first extract minimum will be deleting, so our source vertex yes, U equal to extract minimum Q. And here you can see that the adjacent vertices are T and Y. Then S to T, the value is 10, 10 is less than infinity, therefore infinity will be replaced with 10, and S to Y, okay, S to Y also the previous one you can see the infinity, the direct path is 5, 5 is less than infinity, a lower value will be replaced, and this is the next thing. Okay, you can see here this is the first edge and this is the second edge, and here out of one vertex actually extracted. Okay, all the adjacent vertices are also considered. Now we will go back to the for loop and look for the extract minimum, and extract minimum the priority queue will have only 4 remaining vertices, and which one will be actually deleted from here? The minimum is Y will be deleted. Okay, and Y will be deleted, and you can see the adjacent vertices of Y are, that is very important. Okay, adjacent vertices of Y are T, X and Z. Okay, also you can see the current weight of or the distance of T is 10. Now the distance from Y to T you can see it is 5, the distance of y plus path from y to t. That is 5 plus 3 8. 8 is less than 10. Therefore 10 will be erased with 8 and the predecessor of t will be now y, not s. Previously the predecessors of t and y were s, but now from y you can see that we are finding a smaller path from s to t. Therefore 10 will be erased with 5 plus 3 8 and the predecessor of t will be y, or the parent of t in the shortest path will be y. And here also you can see the next adjacent vertex is set, and 2, the path 2, that means 5 plus 2 7, and this 7 is less than infinity, therefore the distance will be 7. And here you can see the next adjacent vertex is x, the path is 5 plus 9 14, 14 is less than infinity and infinity will be replaced with 14, and parent of x will be y, or predecessor of x will be y, predecessor of z will be y, and predecessor of t also will be y. You can see that. Okay, now 0 and 5, okay, s and y, both are actually extracted or removed from the minimum priority queue. That is why their color you can see in blue. The remaining in the queue are t, x and z. Extract minimum will remove which one? Z will be removed. Okay, extract minimum will be removing the minimum distance variable vertex, that is actually z, with the value 7. Now z will have adjacent vertices s and adjacent vertices x, no other. Okay, only two outgoing edge. Yes, the lowest value 0, therefore no replacement possible, therefore no change for s. And here x you can see the distance of z is 7, then 7 plus 6 is 13. 13 is a better value or less than 14. Therefore x value will be replaced with 13 and the predecessor of x will be z, not y. Just see this. This will be changed. The path will be changed. Now previous path actually removed. Now the shortest path you can see s to t, the shortest path is sy t, and s to z the shortest path is sy z, then s to x the shortest path is sy z x. Now 3 vertices are actually removed from the minimum priority queue. Therefore only 2 vertices are there in the queue and the minimum will be removed, and the minimum is actually t, and t has adjacent vertices y and x, only 2 adjacent vertices y and x, and y the previous distance is 5, then 8 plus 2 10, 10 is greater than 5, therefore no change for y. And here t to x you can see 8 plus 1 9, 9 is a better value compared to 30, therefore x value will be replaced with 9 and the predecessor of x will be set as t. You can see that. You can see that. Okay, now the path will be displayed in dark lines. I hope you are visualizing it. Then the last one removed will be x, and x has adjacent vertex only z, and here you can see 9 plus 4 13 will be the value, but 13 is greater than 7, therefore no change, and this is going to be the final shortest path. And shortest path from s to y is this one, s to t is via y, the predecessor of t will be y, and s to z will be s, y and z, s to x will be s, y, t and x. Okay, this is actually Dijkstra's algorithm, and this is the better algorithm for finding single source shortest path. Okay, and if we go back once again, the initialization will be there except the source vertex, all other vertices distance will be infinity and their predecessor will be nil. Then initially the vertexes added to the shortest path will be empty. Then all the vertices are inserted into the minimum priority queue, and the minimum priority queue always the function will be extract minimum will be deleting the minimum value, and that will be added to the shortest path, and all its adjacent vertices are considered, and we are calling the function relax for checking whether there exists a better path. Therefore relax function is very important. And once again you can see this is the initialization except source vertex, all vertices are having the distance infinity, and they will be, all vertices are there in the minimum priority queue, S will be removed, then as adjacent vertices will be considered, their distances are updated, and again the minimum will be removed, and the shortest path will be always updated with relax. Therefore relax is very important part of Dijkstra's algorithm. And suppose that the priority queue is ordered by linked list, building the queue will have V log V, that is actually sorting, and extract minimum is a linear one, that is order of V. V means how many vertices are actually inserted in the queue. V number of 5 vertices means 5. Therefore the best sorting will be n log n, that is why V log V. Extract minimum will be V, and this is done actually V times. Therefore extract minimum is done V times, therefore V into V square. Each edge is relaxed one time, therefore relaxation is taking order of V. Therefore total time will be V square plus E, that is order of V square. This is going to be that. Now suppose that the priority queue is a binary heap, then building the heap will be order of V, then extract minimum is very fast operation, log V, and this is done V times, therefore V log V, and each edge relaxation log V. Each edge is relaxed one time, that is E log V, and the total time will be V log E plus E log V, and it is actually bigger value will be E log V. Okay, we can conclude with this. Okay, thank you.